GCSE Physics boosters, calculating acceleration. This guy's just jumped off a cliff. He's accelerating downwards. Now, be careful here. There's uniform acceleration and there's non-uniform. Uniform acceleration, in other words, the acceleration is constant. There's a couple of equations which we're going to look at. One of them we've seen already. Non-uniform acceleration, what we do is we have to get the gradient of the velocity time graph. In the last video that was dead easy because it was a straight line. But if it's non-uniform acceleration, then it's not going to be a straight line and we have to do this gradient of a tangent. But let's start with uniform acceleration. And could you remember, you're not allowed to use these unless it's uniform acceleration. I mean, the first equation would give you the average acceleration, but basically these equations are for uniform acceleration. At A level, we do these things called the SUVAT equations. You'll do them in A-level maths as well. SUVAT as in S and U and V and A and T. Anyway, A equals delta V over T. You need to remember that one. This second one, V squared minus U squared equals 2AS. It's on your formula sheet. Okay, so you don't need to learn it, but get used to using it. Practice using it. We're going to do some sums in this video for practice. V is the final velocity. U is the initial velocity, the starting velocity. A is acceleration. S is the distance traveled. Let's have a look at this question. A car speeds up uniformly from 20 to 30 meters per second over a distance of 600 meters. Calculate its acceleration. If you want to have a go yourself, I'll show you my answer in 3, 2, 1. Okay, so the first thing I've done is rearrange the equation. I've said so many times, before you bung in the numbers, rearrange the equation. You're much less likely to get muddled up. So A equals V squared minus U squared over 2S. So that's going to be 30 squared minus 20 squared divided by 2 times 600. Bung in the numbers, work it out, 0.42 meters per second squared. Here's a couple more for you to have a go at. Okay, so pause the video, pen, paper, calculator, get them done. The answers are in 3, 2, 1, and there you go. So on the first one, again, rearrange the equation for S, bung in the numbers, 133 meters, and then for the other one, the time, I've just used A is delta V over T, rearrange that. And in the second example at the bottom, we're working out A, so rearrange the equation for A. You can say minus 7.8 meters per second squared. If it says deceleration, then you don't really need the minus sign. We know it's slowing down. Now, near the surface of the Earth, this guy jumping off the cliff into the water, he survives, don't worry. He's a very good swimmer too. But anyway, near the surface of the Earth, things accelerate due to gravity at 9.8 meters per second squared. This is the acceleration due to gravity, 9.8 meters per second squared. If you dropped a golf ball and a bowling ball off a cliff, they would have the same acceleration. At least for the first few seconds, they would have the same acceleration, 9.8 meters per second squared. A guy called Galileo a few hundred years ago suggested this. People before then thought that heavier things fall faster, and they don't. Okay, the acceleration of an object does not depend on its mass, at least to start with. This idea that he dropped a couple of things off the Leaning Tower of Pisa, he didn't, but some of his students actually did, and he was correct. Okay, all objects fall with the same acceleration, at least to start with. Okay, when an object starts to fall, the only force acting on it is its weight. However, as it speeds up, air resistance gets bigger and bigger. Air resistance increases with speed. And so you've got the force pulling it down, air resistance trying to stop it moving. So the resultant force, which is its weight minus air resistance, the resultant force will get less and less. And in fact, eventually, the resultant force will be zero. Look at this apple. To start with, there's only its weight, but then as it falls faster, air resistance increases because it increases with speed, and then eventually the resultant force will be zero, so its acceleration will be zero. This is a very important graph. You need to understand this graph and be able to explain it. And it's the graph of velocity against time for an object that reaches terminal velocity. Terminal means maximum. It reaches a maximum velocity. This object, it's about 55, no, a bit less, maybe 52 meters per second, looking at the graph. You need to be able to explain the shape of this graph in terms of the forces acting on the object. And my big advice would be have a word-for-word answer prepared. And it's what I said on the last slide about the apple. A word-for-word answer, have it ready. You don't want to have to think in an exam. It's the last thing you want to do in an exam. Yeah, think. So, one note, however, the terminal velocity of an object will depend on a few things. It'll depend on its surface area, because that will affect the amount of air resistance. It'll depend on how streamlined it is, okay? How well it slides through the air, its drag coefficient. And it will also depend on the viscosity of the fluid, because this doesn't just apply to air, it would apply to any fluid. Like if you dropped an object in water, it would reach a terminal velocity. This is an experiment which you should really do. An experiment, now a student investigates the terminal velocity by letting go of a marble at the surface of a liquid. And the liquid might be water, or it might be oil, or it might be something else. And it says she takes a video of the falling marble, and then from the video she takes readings of distance and time. So we've got a table of distance and time, so how far this marble has fallen in the liquid. Calculate the average speed of the marble in each half a second interval, and then how can you tell that the marble reaches terminal velocity? So with my pen, looking here, in half a second. Now, in half a second, it falls 9 centimeters. Then in half a second, it's fallen, the difference is 6. And then in half a second, the difference is 4. Okay. And then in half a second, the difference is 3. And then in half a second, the difference is 3. And then in half a second, the distance is 3. So when we get down to here, every half a second, it falls the same amount. It has reached terminal velocity. An interesting question. If you did this, what could you investigate? What independent variables could you investigate?